Today we are going to again discuss about the optical fiber, the basic theory related to that, and today we'll discuss about ray theory. Okay, ray theory of propagation, propagation of light through optical fiber. Okay. So the theory, as far as the theory concerned with it, it's very much resembles. Okay, the propagation of light through optical fiber. It resembles the theory of plane dielectric waveguide. Okay, and you can apply the same theory of this plane dielectric waveguide to the propagation of light through optical fiber. Okay, so we'll just understand this is the cross-sectional view of lateral cross-section, rather, what you can say. This is the cladding, okay, where this is the core refractive index N1, and again this is the cladding of the refractive index N2, and obviously the refractive index of N2, the cladding, has to be less than N1, okay, so that they can occur the phenomena of total internal reflection. So without going into this particular aspect, because planned dielectric waveguide, you can go through any electromagnetic book, you will get over there. Our concern is something different, so we'll focus to that. Okay, so we can just understand that an important parameter of an optical fiber, that is numerical aperture, okay, could be derived using the ray theory of the ray theory propagation of light, okay, as we'll discuss right now. So we'll consider a ray. We'll just draw a diagram, or a diagram over here further. I will just as we have done earlier, we'll just draw it over here. You can see again this will be the core part as usual. So this is N1, obviously this is N2, and this is N2. Okay, and N2 is obviously less than N1. So what we can say is that we'll allow the light. Okay, we will consider a ray of light entering into the core of a step index optical fiber, and this is the ray of light, okay, making an angle phi. Okay, this ray makes an angle phi with respect to the normal at the core surrounding medium interface. Okay, let a part of this energy associated with the ray which has entered the core get reflected into the core from the core cladding interface. So what I want to say is that it strikes the core cladding. This is the core cladding interface. A part of it will go this side, and there will be a part of it coming inside the core, back to the core. So this is 90 minus again theta 1. By the simple geometry you can understand it very well. This is the core cladding interface. For your understanding, this is the core cladding interface. Okay, so now the figure is clear. Okay, so the other part, it get see here, one part is getting into the back into the core, and the other part it goes transmitted into the cladding. Okay, and let this makes an angle theta 2. Okay, with respect to the normal at the core cladding interface. So this is the normal over here, and this is the normal over here. Okay, so from Snell's law, okay, we'll apply the Snell's law, the two surfaces here and here. Okay, so from here we can assume the refractive index to be N for this surface. This one N1, this one is N2, and obviously if we'll talk about this one, again it's N. So we'll consider this part, Snell's law. So for this part we'll write N by N1, okay, is equal to cos theta 1 by sine phi. This is say phi, okay, we'll consider this to phi. This is equation number 1, and for this part we'll write N1 by N2 is equal to sine theta 2 by sine theta 1. So as far as this cos theta 1 is concerned, basically we are writing sine 90 minus theta 1. Okay, from here you can see it's sine 90 minus theta 1 by sine phi. That is okay, sine r by sine I. That is what I have mentioned over here. But instead of writing sine 90 minus theta 1, I have just written here cos theta 1 in a single step. Okay, so there has to be no confusion as such. Okay, now substituting for theta 1, okay, from equation 2 into equation 1, it gives us an expression for phi. So phi, if we substitute theta 1, the value of theta 1 from this equation into this, we'll get what? See, we'll get phi equal to sine inverse. Okay, we'll write n1 cos, again give a bracket, sine inverse, okay, n2 by n1 sine theta 2, close the bracket, whole bracket by n. So this is your equation number 3. Using the trigonometric condition, okay, we'll apply the trigonometry. We can write it like cos, we know this, cos x is equal to under root 1 minus sine square x. So we'll use this particular thing in equation number 3 here. So we'll write, now here we'll write phi equal to sine inverse, okay, n1 by under root 1 minus n2 by n1, and this is n2 and this is n1, okay, that's right, n2 by n1 sine theta 2 whole square, okay, by n, close the bracket. So this is n1, okay, this is n1. So this is equation number 4. Now if the ray is incident at core cladding, okay, we'll just write over here, if the ray is incident, okay, at the core cladding interface, okay, makes the critical angle, then theta 2 will be equal to pi by 2 radian, and hence phi, this phi will be, if theta 2 is pi by 2, then phi will become sine inverse under root n1 square minus n2 square by n. So you will get this much, phi is equal to this much. The physical significance of this phi, okay, the physical significance of phi is that any ray of light which enters the fiber core at an angle less than phi, okay, as given here in this particular equation, say this is equation number 5, okay, would undergo total internal reflection at the core cladding interface, which is very, very important for the propagation of light, that there from here this part it has to go total internal reflection, and for this particular thing it has to meet this condition, okay. So it would go undergo total internal reflection at the core cladding interface and thereby remain trapped in the core in the course of its propagation through the fiber, okay. Thus the value phi given by equation 5 for a given fiber is aptly, this could be written as, this could be referred as, this phi is referred as maximum acceptance angle of that fiber, okay. So the numerical aperture is now defined from equation 5. The numerical aperture is expressed as n sine phi, which is equal to under root n1 square minus n2 square. So this is the definition for NA, that is n sine phi. We'll put the value of sine phi from this particular equation. Sine phi is equal to 1 to n1 square by n minus n2 square by n, and will get cancelled out, and ultimately we'll get this much. So this is your numerical aperture. So we'll just meet in the next lecture with some new topic related to optical fiber. Until then, thank you.